So we discussed about standing wave antenna, general standing wave antenna. What is small antenna that we discussed. Then we discussed earlier we discussed about Hertzian dipole antenna. Finally, we will come to the half wave dipole antenna. The length of a half wave dipole antenna is equal to half the wavelength. So L is equal to lambda by 2. If you take L is equal to lambda by 2, then K into L is equal to, K is 2 pi by lambda. So 2 pi by lambda into lambda by 2. So that cancels out, so lambda cancels out, 2 cancels out, leaving you pi. So KL is equal to pi. So for a half wave dipole antenna, this will correspond to L is equal to lambda by 2 or KL is equal to pi. If that occurs, then we call it a half wave dipole antenna. Each arm of the dipole antenna, length of each arm is lambda by 4. This also you can say H is equal to lambda by 4. This is one of the most common antennas in use. Z limit on the Z is from minus lambda by 4 to plus lambda by 4. That is the limit on Z. It extends along the Z axis. So current distribution will be of this, from standing wave current distribution I will take, which is Iz is equal to I, which is the peak current, into sine K into L by 2 minus absolute Z. Now if I put K into L by 2, K into L by 2 is pi by 2. So sine pi by 2 minus Kz is cosine Kz. So Iz is equal to I cosine Kz. Many books you will find Iz is equal to I cosine Kz. Many books you will find Iz is equal to I sine K L by 2 minus absolute Z. Both are correct and both are one and same. So it is up to you which one you are going to use. I use the first one because that is common to standing wave antenna. So if I do that, that is common. So everywhere I can put that the analysis I can use for all antennas. That is why I use the first one. Now first thing is we will find out the field. So calculation of field for a half wave dipole antenna will start with this. For field we know E, electric field, is equal to 1 by j omega mu curl of A in a source free region, that we know. So A is equal to, we know, 1 by 4 pi integration j r dash exponential minus jk capital R by capital R integration over the volume. Capital R is the distance between the source to observation point. So that we know, capital R is equal to R minus R cap dot R dash. So if you put that in the numerator, we can neglect that R minus R cap dot R dash. The second part, minus R cap dot R dash, that we can neglect in the numerator because that is almost negligible compared to R. So that is contributing to amplitude. The contribution to amplitude is almost nothing due to that, so that we can neglect. In the numerator, it is in the exponentiation. Since in the exponentiation, therefore we cannot neglect that. For the numerator, we take it as R minus R cap dot R dash. This we have already discussed. So using that, this we say that AR is equal to mu into exponential minus jkr by 4 pi r j r dash exponential jk dot r dash integrated over the volume. From once we know A, we can find out that is the radiation vector F. So Fk will be only the integral part. So integration over volume of j r dash exponential jk dot r dash, that is F. Then we say that A is equal to mu exponential minus jkr by 4 pi r into F. Now F is a function of K, theta and phi. K we are not concerned because once we fix the frequency, K is fixed. So K we are not concerned. So variation of F is with respect to theta and phi. So F varies as theta and phi. Then curl of A is equal to minus jk cross A plus the terms which are of 1 by r square, 1 by r cube, etc. These are called higher order terms. So they are neglected. So only curl of A is taken as minus jk cross A. This we have seen earlier, so I am not going to repeat this. Now we have already seen curl of A is equal to minus jk cross A. Using that, the expression for electric field E is equal to minus jk eta exponential minus jk r by 4 pi r cap cross F cross r cap. That we can write, and H is equal to minus jk, only eta will drop out, and r cap cross r cap will drop out. So H is equal to minus jk exponential minus jk r by 4 pi r cap cross F. So this all these we have already seen when we started the antenna field distribution. So all these we have already seen. We are going to use them. So let us start with the radiation vector F. In this case, F is equal to integration minus h to h I sin k L by 2 minus z dash absolute exponential j k z dash cos theta dz. Now use, as in the previous case, use the same identity from the integration table, and that will give us Fz is equal to Fz is equal to 2I by k cos kh cos theta minus cos kh by sin square theta. This we have already seen. Now put h is equal to lambda by 4 and k is equal to 2 pi by lambda. If we put these two things, cos kh is equal to 0. So cos kh 0 is equal to 0 means f is equal to 2I by k remains as it is, cos of pi by 2 into cos theta by sin square theta. So that is what it is, Fz is equal to. Now using that in the Fz, we will get Fz is equal to this term, exponential jkj. This is another alternative method of finding Fz. I am not going to discuss this. Let me leave this out. I will provide the notes. If you do not understand this, you can ask me. So Fz we have found out that Fz we have found out to be of the form 2I by k cos pi by 2 cos theta by sin square theta. This is the form of Fz. It depends only on theta. It is not dependent on phi. Okay. Next, the expressions for field now will be E is equal to theta cap E theta. This we have seen. So that will be theta cap jk eta exponential minus jk r by 4 pi r Fz sin theta. H is equal to phi cap h phi, which is equal to phi cap jk exponential minus jk r by 4 pi r Fz sin theta. Fz expression we have found out. Just put the expression for Fz, we will get all the terms, the expressions for E theta and H phi. Now, what will be the radiation pattern? If you look at this, these expressions, the expression goes to maximum when theta is equal to pi by 2. And in this case, normalization constant Cn is equal to 1. So radiation pattern is again figure of 8. You can see the two radiation patterns. One is in the top and bottom. In the top we see the absolute gain. Absolute gain means maximum is 1. So you take the gain and divide it by its amplitude, maximum amplitude. So that will be 1. Then it goes down. Similarly, in the bottom it is in terms of dB. So although the upper one looks narrower, it does not have a higher directivity because these are on two different scales. But both of them are same thing. Okay. Now intersection of 3 dB point or half power circle with the gain pattern. These are called the gain pattern. With the gain pattern, that gives us 3 dB to be equal to 50.96 degree. So 3 dB angle occurs half power beam width, that comes from this 3 dB angle. So 3 dB is 50.96 degrees. So half power will be 180 minus 2 times 3 dB. So that will be 78.08 degree. So that is the half power beam width. Once you get the half power beam width, then you can find out the fast null beam width, which is approximately 2 times the half power beam width. These beam widths are narrower than the Hertzian dipole, because in the Hertzian dipole the beam width is 90 degree, because that varies as sin theta. Now if you have sin theta variation, sin theta maximum occurs when theta is equal to pi by 2, so that is the maximum power. Then power becomes half, means E becomes 1 by root 2. So from 1 to 1 by root 2, sin becomes 1 by root 2 when theta is equal to pi by 4 or 45 degree. So since it is 45, so 45 in the other side 45, so 2 times 45 is 90. 180 minus 90 gives you 90. So Hertzian dipole or small dipoles, you get it around 90 degree. For half wave dipole it is 78 degree, almost 78 degree, 78.8 degree. Then we'll come to the radiated power. U, or the intensity, is equal to this, we know, 1 by 2 r square E theta square by eta. That will be equal to 1 by 2 eta I square by 2 pi square cos square pi by 2 cos theta by sin square theta. So because we know what is E theta, just put the values of E theta there, we are getting this expression. So that is U theta. Now you can ask me from where I got U theta is equal to 1 by 2 r square E theta by E theta square by eta. Just look at the definition of U theta. So from that you will get U theta or dp by r square d omega, that gives you PR, and from that definition r square into PR, from that definition we get U theta. So that is from where we get this. Now P rad is equal to integration over theta from 0 to pi, integration over phi from 0 to 2 pi, U theta sin theta. So that is P rad. Now integrate it, U theta we know. So if you integrate it, put the values of U theta. So you will get the amplitude part, which is not integrated, which is not to be integrated, which are constant. Those will be 1 by 2 pi, 1 by 2 into 2 pi, eta I square by 2 pi square. Then the integration part. The integration is not possible to do it manually. You require a numerical technique to integrate this. So using numerical technique, that integration value will give you 1.2. I am taking more accurate. Here is 1.2188 or 1.22. But you can take as 1.2. Remember, this integration gives you 1.2 or 1.22. So now put these values, everything, all the value 1 by 2, 2 pi, 125 by 2 pi square into I square into 1.2. So that will give you 36.5640 I square. So that will be the radiated power. Once we know what is the radiated power, we can find out what are the input impedance and directivity. So to find out input impedance, we know Iz is equal to I sin KL by 2 minus Z. So sin KL by 2 is equal to 1. That implies that sin square KH is equal to 1. Sin KL is equal to 0 implies that cos KL is equal to minus 1. Use these two. If you use these two, then find out what is Rin. Rin is equal to R peak by sin square KH. This we have derived. So that you can write as Rin is equal to R peak. Why? Because sin square KH is equal to 1. We already have seen here. Sin square KH is equal to 1. Since sin square KH is equal to 1, so Rin is equal to R peak. If we put, then we have to find out what is R peak. We can see the expression for R peak at the bottom. R peak is equal to eta by 2 pi integration 0 to pi cos KH cos theta minus cos KH whole square by sin theta d theta. Then Rin is equal to R peak, that you can write as eta by 2 pi integration 0 to pi cos pi by 2 cos theta square by sin theta d theta. If you integrate this using numerical method, that is going to give you 73.0790, which is approximately 73 ohms. So input resistance for a half wave dipole is 73 ohm. Now why it is useful? Reason is why half wave dipole is so popular. Reason is input impedance is 73 ohm. If it is 73 ohm, then it is equal to almost same as the characteristics impedance of a transmission line that we are using, coaxial cable, etc. There it is almost same. So it is easy to match the feed line. Now Dmax is equal to eta by pi r peak. R peak we know, so you can find out what is Dmax. Dmax is equal to 4 pi U max by P rad. Next. That you can put 4 pi by 8 pi square eta I square into 1 by 36.5650 I square. So once you put those values, then that will give you 1.64. So Dmax will be 1.64. For a dipole, this is for a simple dipole, half wave dipole. Dipole, it is D dipole is equal to 1.64 in absolute term. If you go to dB and compare it with a dBi isotropic dipole, so it will be 1.64 by the directivity of isotropic dipole, which is 1. So you take that, and that will give you a 2.15 dBi. dBi, I stands for isotropic. So the ratio is taken with respect to isotropic dipole. So that again is equal to 0 dB, because dipole, when you take its ratio with respect to itself, so that ratio will be 1 log of that whole. Log of 1 will be 0. So D dipole is equal to 0 dBd. Small d at the end of B stands for dipole. So 0 dBd. Then radiation resistance will be 2 pi rad by I square. That will be equal to 73.1280 ohm. That will be the radiation resistance. Then Z in dipole will be, in most of the books you will see that Z dipole, Z is the input impedance. So input impedance of the dipole will be equal to 73 plus J 42.5. It is not 73.1280 ohm. It has an inductive term. We will discuss why it has an inductive term in the next class, when we will consider when we will go to discuss the design considerations of dipole antenna. But remember, dipole Z dipole is equal to 73 plus J 42.5 ohm, and on that we can make, if we try to remove this inductive part by making some adjustments in the dipole design, then Z dipole becomes almost 70 ohms. Not exactly 70 ohm, it will be 68, 69 ohms, something like that. So that will be the input impedance of the Z dipole. Then in this, since it is a conductor, we have a conducting wire, therefore that will have ohmic losses. So it will have a ohmic loss will come because of the resistivity, ohmic resistivity. So R ohmic is equal to Rs by 2 pi A lambda by 4. Rs is the resistivity, and A is the diameter of the dipole, or diameter of the arm. So 2 pi A gives you the perimeter of the arm. Lambda by 4 actually gives you L, length of the arm. So that is lambda by 4. So Rs by perimeter into L. So Rs by D into L. So in that form R ohmic comes. So with this we will come to the end of today's lecture. We will discuss about design aspects, etc. in a subsequent class. If time permits, we will discuss those things. Next class, maybe we will discuss design, or maybe we will discuss antenna array. Okay. This will stop. बंद कर दिया.
सर नमस्कार.
हाँ को.
Sir, I am very sorry, sir. सर ମୁଁ ଇଂଲିଶ ପଢିପାରିଲିନି ସାର୍। ସାର୍